to know the planet, to know the universe, to find out what makes things work and why things are the way they are through observation, study, and experimentation. We can unleash the power of the universe and make almost anything happen. This is Understanding Science.
There are few things that affect us as much as the weather. All life on Earth depends on it. And knowing what the weather is going to be like helps us plan for tomorrow. Hi, I'm Dr. Science. There are scientific explanations for our weather: rain, snow, heat, tornadoes, hurricanes. And to understand what causes our weather, we must go way back to the very origins of the Earth, to the very beginning of our weather systems. Today's scientists help us study changes in the Earth's early atmosphere by analyzing dust trapped into the ice of Greenland. Before the Earth's atmosphere, as we know it, was formed, the only creatures that could survive on the planet were microscopic organisms living well below the surface of the oceans. Scientists speculate that about 3.8 billion years ago, the heat of the sun triggered a chemical reaction among methane, ammonia, and water. This reaction formed new materials such as nitrogen, hydrogen, and carbon dioxide. The hydrogen was so lightweight that the Earth's gravity could not hold it, and it escaped into space. This left lots of nitrogen, carbon dioxide, and some water vapor. As the sunlight continued to beat down on the Earth's atmosphere, the water vapor broke down into oxygen and hydrogen. Again, the lightweight hydrogen escaped. The oxygen atoms that were left over then began to combine together to form ozone. An ozone molecule is really just 3 atoms of oxygen joined together. This buildup resulted into a layer of ozone between 19 and 30 kilometers above the Earth's surface. The ozone layer absorbs most of the sun's harmful UV radiation and is a protective shield for living things. It is something like an umbrella for life on Earth. After the ozone layer developed, a new group of living organisms appeared: blue-green algae. These organisms were the first to use energy from the sun to produce food through the process of photosynthesis. The food made by the algae was used for growth and development. The waste product of photosynthesis was oxygen. Oxygen from this process combines in twos and stays at the bottom of the atmosphere. Photosynthesis is what caused the oxygen in the Earth's atmosphere to increase. That is how the oxygen was formed, that we and all animals would one day use to breathe. Our atmosphere today is made up of 78% nitrogen, 21% oxygen, and 1% trace gases such as helium, krypton, and xenon. In the past 4 billion years, the composition of the atmosphere has changed, and so has the temperature. When you travel at high altitudes, your lungs have to work harder to supply your body with oxygen. The higher up we go, the thinner or less dense the air gets. The air up here also gets colder. Here's an experiment to show us how altitude affects our density and temperature. All we need are marbles, a small saucer, and a large plate or tray. Divide the marbles into 2 groups of 20, and imagine that each marble is a particle of air. Now, place 20 marbles into the small saucer and put them as close together as possible. Place the remaining 20 marbles on the large plate or tray and spread the marbles as far apart as you can. In which container is the density of the marbles greater? The density of marbles is greater in the small saucer because there are many more marbles per unit of space. The marbles in the small saucer present air particles near the Earth's surface and are arranged more densely. The marbles in the large plate or tray represent air particles in the atmosphere many kilometers away from the Earth's surface. Based on our experiment, why do you think mountain climbers sometimes need oxygen masks at high altitudes? Well, At high altitudes, there are simply less air particles in a given amount of space. Since air contains oxygen, there would also be fewer oxygen molecules available at a high altitude. Scientists also divide the Earth's atmosphere into layers based on temperature differences. The troposphere is the lowest layer of the atmosphere. Now, this is where the Earth's water vapor is found. From the planet's oceans, lakes, and streams rises water vapor into the troposphere. As the water vapor rises, it begins to cool, forming clouds. Eventually, the water vapor will return to the Earth's surface as rain, snow, sleet, and hail. Fierce winds also blow in the troposphere, and it is often called home of the weather on Earth. Just above the troposphere is the stratosphere. In the lower part of this layer, the air temperature remains constant and very cold, around -60 degrees Celsius. The temperature in the upper portion of the stratosphere is warmer, around 18 degrees Celsius. Now, this is because most of the ozone layer is found in the upper portion of the stratosphere. And as the ozone layer reacts with the UV radiation, it gives off heat. The upper portion of the ozone layer spills into the mesosphere. In this layer of the atmosphere, the sun's radiation breaks down ozone molecules into free oxygen atoms. It is in this layer of the mesosphere that the ozone layer ends. The temperature then drops steadily as the altitude increases. The highest section of the atmosphere is the thermosphere, the Earth's outer frontier. This layer also contains a region known as the ionosphere. Radiation from the sun causes ions, or atoms, that have electric charge to form this region. As the atmosphere's highest layer, the thermosphere also marks the beginning of outer space. So, what does the Earth's atmosphere have to do with our weather? Well, the weather is caused by the interaction of several factors. Heat, energy, air pressure, winds, and moisture. Let's find out what makes the atmosphere warmer. Almost all energy on Earth comes from the sun. This is the radiant energy and helps warm the Earth. Also, the atmosphere helps warm the Earth by absorbing, storing, and recycling the sun's radiant energy. If radiant energy is neither reflected nor absorbed, it reaches the Earth's surface and is then absorbed by the Earth and changed into heat. This heat energy then travels back from the surface of the Earth out to space, thus warming the atmosphere. If the whole atmosphere is warmed by heat rising from the Earth, why is the temperature in Florida so different from the temperature in Alaska? That's because radiant energy strikes the Earth at different angles, causing uneven heating of the Earth's surface. The greatest heat is where the sun's rays are the most direct. So, areas near the equator, like Florida, have higher temperatures. The sun's energy is spread throughout the atmosphere in three ways: conduction, convection, and radiation. Conduction is the direct transfer of heat energy from one substance to another. Soil, water, and air are poor heat conductors. And conduction plays only a small part in the spreading of heat energy through land, sea, and atmosphere. The sun's energy is also spread through convection, the transfer of heat in a fluid. Air is a fluid. When air near the Earth's surface is heated, it becomes less dense and rises. Cooler, more dense air sinks. When warm air rises and cool air sinks, convection currents are formed. These convection currents in our atmosphere cause our weather. Now, let's do an experiment to see how convection currents work. First, pour water into a small beaker until it's almost full. Then heat the beaker, holding it about 10 centimeters above the flame. Then add 2 or 3 drops of food coloring to the surface of the water. The convection currents in the water cause the food coloring to swirl about. The warm water rises as warm air does in the atmosphere, causing the food coloring to swirl, much like convection currents. The sun's energy is also spread through radiation, or the transfer of heat energy in the form of waves. Infrared radiation, or heat energy from the sun, is absorbed by soil, water, plants, and animals on the Earth's surface. Most of the heat energy on Earth is spread through the radiation process. In the atmosphere, there is also the factor of air pressure, and that affects our weather systems as well. Scientists use a barometer to measure air pressure. When the air pressure increases, the column of mercury rises in the barometer tube. When the air pressure decreases, the column of mercury drops in the tube. Evangelista Torricelli invented the barometer, which is an essential instrument for finding out how our weather systems work. First, let's see how low air pressure causes clouds to form. In the upper atmosphere, when large masses of air move apart, the air pressure is reduced on the layers of warm air below, and the warm air rises. If the warm air rising is moist, clouds will form in the upper atmosphere. These clouds, formed during low air pressure systems, can lead to rain, snow, sleet, and other bad weather. When large masses of air come together in the upper atmosphere, air pressure may become high. The air masses press down on the layers of air below and usually prevent warm, moist air from rising into the upper atmosphere. So, when air pressure is high, clouds do not form and often mean we will enjoy fair weather. Now we know that when the barometer reads low pressure, there could be some clouds in the forecast. When you get a high pressure reading, you might expect clear skies. But the weather system sometimes is difficult to predict, and there are exceptions to the air pressure's effects on it. Winds are formed by movement of the air. When air is heated, its density decreases. So warm air rises and produces an area of low pressure. Cooler, denser air moves underneath the rising warm air. Winds are formed by this movement. There are two types of winds. Local winds blow from any direction and cover short distances. Global winds blow from specific directions and usually travel long distances. However, both are caused by differences in air pressure from the sun's unequal heating of our atmosphere. Another factor of our weather is humidity, or moisture in the air. The sun's radiant energy turns Earth's liquid, water, into a gas. When the water evaporates, the atmosphere gains moisture or becomes more humid. Relative humidity is the percentage of moisture the air holds related to the amount it can hold at a particular temperature. So, which do you think holds more moisture and humidity? A, warm air, or B, cold air? The answer? A. Warm air can hold more moisture and humidity. When the air reaches a certain temperature, or dew point, moisture in the air turns into droplets. This process, which forms clouds, is called condensation. The condensed water from the clouds often falls to Earth as rain, snow, sleet, or hail. Water that falls from the atmosphere is called precipitation. It's getting foggy in here with all this condensation. Let's make some of our own fog in this weather experiment. First, fill a narrow-necked bottle with hot water. Pour out most of the water, leaving only about 3 centimeters in the bottom. Take an ice cube and put it in the mouth of the bottle. See the fog that forms? Now, let's try it with the same setup and use cold water in the bottle. Add the ice, and no fog. Why does fog form in the bottle with hot water, but not in the bottle with cold water? The fog forms in the bottle with the hot water when the water vapor in the air and from the hot water rises and condenses. As it reaches the ice cube, the cold water was the control of our experiment. Now on to one of my favorite weather subjects. Clouds. There are three main types of clouds: cumulus, stratus, and cirrus. Cumulus clouds look like piles of cotton balls in the sky. They're very fluffy and have flat bottoms. Cumulus clouds may indicate fair weather, but sometimes they develop into larger clouds that produce thunderstorms. Stratus clouds are gray, smooth clouds that cover the sky and black out the sun. When they form close to the ground, they're called fog. When you see clouds that are very feathery and fibrous, they're cirrus clouds. Cirrus clouds form at high altitudes, and you usually see them when the weather is fair, but they often indicate rain or snow within several hours. Storms are violent disturbances in the atmosphere. They are marked by sudden changes in air pressure and rapid air movement. Thunderstorms develop from cumulonimbus clouds. These clouds form when there is a rapid upward rush of warm air from very hot areas on the ground and a rapid downward movement of cool air around the warm air. In the upper portion of the cloud, water droplets freeze into snow and ice crystals. When the crystals fall through the clouds, they chill the water droplets in the cloud and cause them to form larger drops and fall. The usual result is a downpour of rain, along with thunder and lightning. Oh, by the way, thunder and lightning occur essentially at the same time. Lightning is caused by the buildup of negative electric charges at the bottom of a thundercloud. When we say a negative charge, that means that the molecules there have extra electrons compared to the molecules on the ground. The charge builds up until it reaches a point where the air can no longer block the passage of electricity. Then there is a flash of electric energy between the cloud and the ground, or from cloud to cloud. This energy is lightning. As the electric energy passes through a section of air, it heats the section, causing a violent movement of air. This sharp and sudden movement produces a booming sound, thunder. Occasionally, ice crystals falling through a thundercloud are caught and tossed back up. In the process, water droplets freeze into the crystals, making them bigger. Eventually, they get so big and heavy, they fall to the ground. This is called hail. The most violent storms on Earth last only a few minutes. The tornado. A deadly tornado is a major weather hazard. It is formed when the air spins out of the base of a thundercloud. At the bottom of this swirling funnel, the air is extremely low in pressure. When this low pressure point touches the ground, it acts like a giant vacuum cleaner. Dust, soil, trees, animal, cars, even people may be drawn up into this dangerous tornado and whirled around. But the storms with the most energy are hurricanes, the greatest storms on Earth. Hurricanes usually occur in late summer or early fall over the tropical waters of the Atlantic, just north of the equator. The warm air there heats the air above it and creates updrafts of air currents. The air pressure is low in the center of the updraft. In the northern hemisphere, this causes a swirling counterclockwise movement of air around the low pressure center. As time passes, more and more warm air is drawn up into the center of the system. As the air rises, it spreads out, cools, and swirls down into the low pressure center, or tropical cyclone. The air moves faster and faster. Rising warm air adds energy to the system. When the wind speed reaches 117 kilometers per hour, the storm is, right, a hurricane. We still have time to find out how air masses create the fronts of air with different temperatures and levels of humidity. Air masses are changes in the weather caused by movements of air. They have the same temperature and humidity throughout. 4 types of air masses affect weather in the United States. Maritime tropical air masses form over the ocean near the equator. The masses hold warm, moist air and bring very hot, humid weather. Maritime polar air masses form over the Pacific Ocean in both winter and summer. Now, they form in the North Atlantic waters in summer and bring cooler temperatures and fog to the eastern United States. Continental tropical air masses form over land in Mexico and bring very hot, dry air. Now, when the two air masses meet, a front forms. There are 4 types of fronts that affect our weather. Cold fronts occur when a mass of cold air meets and replaces a mass of warm air. Violent storms are associated with cold fronts. A warm front happens where a mass of warm air overtakes a mass of cold air moving over it. A warm front is usually accompanied by precipitation, with hot, humid weather to follow. An occluded front occurs when 2 fronts, one hot and one cold, meet. This front doesn't produce extreme weather as cold and warm fronts do. The last type is the stationary front, when a warm front meets a cold front and there is no movement. Rain may fall for many days when a stationary front occurs. The systems that create our weather are fascinating to study. For some people, like meteorologists on TV, forecasting weather is their job. Now, the next time it's cloudy, rainy, or sunny outside, think about the weather systems and see if you can figure out what weather is coming up next. I'm Dr. Science. Hasta la vista, baby.
This program has been a presentation and production of TMW Sales Company. For information on other programs offered by the company, contact the phone numbers on the screen.